Welcome back, everybody, and welcome to us changing topic. So we had discussions of discriminative methods, which can also be used as generative methods. So when you solve differential equations with neural networks, you actually generate a new solution. But the basic philosophy is a little bit different from what comes now, and that is the topic we are going to enter now for the rest of the semester, which is going to rotate around generative models. Now, in the beginning of the slides here, and I will not touch so much this topic, you will find examples of the autoencoders and how you can implement them with TensorFlow and Keras and PyTorch. So the basic message with an autoencoder, beyond it being a very popular method, is that this is an efficient way to reduce the dimensionality of a problem. And last week, we made a mathematical link with the principal component analysis method, which is also one of these popular methods for reducing the dimensionality of the problem. So the codes which are here, especially those in both TensorFlow and PyTorch, are pretty simple. And they normally just involve one or two layers. And you will see examples of where we use both recurrent neural networks, convolutional neural networks. So the decoder part and the encoder part could be not only a neural network, but it could be a convolutional neural network, a recurrent neural network, etc. And you will see that the example which you will find in these TensorFlow and PyTorch codes is essentially these autoencoder methods applied to the MNIST dataset. But it should give you roughly the kind of rough feeling of how you would use them. And if you're dealing with dimensionality reductions and you are having datasets with huge dimensionalities, then autoencoders is a very useful method. So I would typically recommend taking a look at that if that is of interest for your thesis work, in particular if you have large dimensionality. Okay, so I wanted to jump into the topic which we are going to deal with now, and that's first an overview of generative models, and then we are going to look at the basic elements, the basic mathematics, which we need to deal with, and we are going to list the methods we will study, and then we need to say a little bit about how we do the calculations. So what comes to our rescue is Markov chain Monte Carlo sampling. That's the way we are going to sample these probability distributions. So that means that the Markov chain Monte Carlo methods, they are the methods which in a sense have saved the day for these generative methods. And when we are proposing a new move, typically you have a sampling rule, and this sampling rule, a famous one, is given by the Metropolis Hastings algorithm. So we will cover some of the basics. For those of you who are not fully familiar with the Markov chain Monte Carlo methods, that is the way you would sample these probability distributions. And you will see why we need Markov chain Monte Carlo methods. Then, if we get time, we will start diving into one of the first generative models, which is called Boltzmann machines. And this is something which was proposed almost 45, 50 years ago. And Hinton, when he got the Nobel Prize, one of the parts of the Nobel Prize was based on the work on Boltzmann machines. So there are some reading recommendations. I'm going to not go through the codes because I'm going to leave that to you guys, but you will find codes here where you can test the MNIST dataset. There is an encoder and decoder where you reshape everything with convolutional neural networks. That's an example applied to the MNIST dataset. There is a recurrent autoencoder. Recurrent networks are not the optimal ones for this type of tasks. And at the end here, there's also a code in PyTorch, which does a similar analysis using the MNIST data. And you can see it's loading the MNIST dataset. It splits in train and test, and then has a decoder part and an encoder part. And these are the steps which are then included. This is a simple, shallow neural network as a decoder part and encoder part. So I leave that to you guys to take a look. I mean, it takes some time to run these codes. But I wanted to say now a little bit about the overarching inputs to generative methods. So generative methods play a very important role in essentially all modern applications. So if you look at programs like DALL-E to draw images or similar programs, they are based on things like diffusion models. So in the generative model is a branch of machine learning that involves training a model to produce new data that is similar to a given data set. And what we actually do then is to train a probability distribution. And this is something which we looked at in the very beginning of the semester. So what we are going to produce then in here in these generative models is a probability distribution, which we then can use to produce, let's say, new images of horses, as seen here. So this breaks a little bit with the philosophy which we had with the discriminative methods, where we often have a data set. It could be supervised or unsupervised, and then we train a model to make predictions. Now, when you have created a probability distribution, you can actually do more. So you can fit some data. You can find correlations in the data set, as we discussed last week. We can set up the correlation matrix. We can calculate the covariance matrix and all these measures to find information about the data and how strongly correlated some features are. But when you have a probability distribution, you can also look at causation. So you can say, what is the probability of A given B? You can also estimate the error of your parameters. This is something you cannot do in a rigorous manner when you look at the standard implementation of a neural network, unless you are solving a differential equation where the solution can be interpreted as a probability distribution. So if you solve Schrödinger's equation with a neural network, then you get the wave function, and the wave function squared is a probability distribution. But in general, the standard discriminative methods, they are more limited to you making predictions and finding correlations in the data set. When you now move into the generation of a probability distribution, this is actually something which is more interesting to most scientific applications, because you want to make predictions as before. You want to find correlations in the data set. You want to estimate the error on your parameters. This will be new. And then you also want to find what is the probability of a given event given an event B. What's the probability of A given B? So this means that we are going to be really at the interface between what traditionally is called a frequentist approach in statistics, where you essentially try to fit a probability distribution from the frequency of your data, or you don't care about the probability distribution, and what's normally called a Bayesian approach. So after these initial kind of remarks, we are going to remind ourselves about some basic statistic theorems. And one of these is Bayes' theorem. So Bayes' theorem plays the same role in statistics as Pythagoras does in geometry. So it's a fundamental theorem in statistics. And when we move from Boltzmann machines to variational autoencoders, you're going to see that this actually mixes in all of the elements which we are familiar with from Bayesian statistics, although I know that many of you may not have taken a course in statistics. So I'm going to remind you of some basic elements before we then move to the problem with generative methods. So the problem with generative methods, the main problem is that we have a probability distribution, which is a probability distribution over many, many features and variables. So if you are modeling, let's say, the probability of finding a neon atom in a given state, and you take away all the atomic nuclear degrees of freedom and you leave only electrons, you have 10 electrons in atomic neon and 3 degrees of freedom. So that means that your probability distribution is a 30-dimensional object. Often, a probability distribution can be a million-dimensional or even more dimensional, higher dimensionalities for the probability distribution. Then to sample from that one becomes difficult. So these are the kind of bottlenecks which we will address. But let's move on a little bit. So the basic message is that we want now to train some probability distribution, which does a good job in, let's say, making images of horses, just as an example. And these models have actually improved considerably. So just some few years ago, you would get the horses with 6 legs, 10 toes or whatever. But nowadays, if you have used software like DALL-E, for example, or any of these plotting softwares which are around, you will see that you can get pretty good images when you just write in the prompt, write a drawing or make a figure of the Dolomites, for instance. It comes out pretty nice. Okay, so let's just scroll down a little bit before we switch to the whiteboard. So in order to build such a generative model, we would typically require a data set which consists of many examples. And this is known as a training data, and one such data point is often called an observation. And each observation, as you know, can contain many features. So if you want to draw images of horses, you will need to have the legs, the tail, the head, the rest of the body, the color of the horse, etc. So these will be the many features which you want to train in such a model. So conceptually then, for this image generation, this is normally a pretty difficult task. And if you think of the enormous ways that individual pixel values can be assigned and the relative tiny number of such arrangements that constitute an image. We, just to quickly remind you of discriminative models, this is again taken from this textbook by Foster, where you will find lots of examples on the usage of generative models in TensorFlow and Keras. It actually has a pretty well-developed library of Jupyter notebooks, which I would strongly recommend. So if you look at what we did typically with a CNN, we would train on images of paintings on Van Gogh, and then we would train a model which gives us 1 if this is a Van Gogh painting and 0 else. And then we would feed in a new image, like the one you see to the right here, and then you would like to make a prediction on whether that is a Van Gogh or not. So that could be a typical example of what we have done till now. So when we look at discriminative models, this is something which is often seen as this traditional machine learning part. But generative models are actually the models which are, I would say, from my point of view, with respect to what I'm doing, the more interesting topic. So let me just shrink a little bit the image here. And the different models which we are going to look at, and you can take a look in the textbook by Foster here, because the different chapters contain then different description of various methods. So we are going, when it says density here, this is the probability density function, or just the probability. So I will often just call it the probability. And in this case, as you will see from Boltzmann machines, which belong to the class of energy-based models, we are going to start with an explicit expression for the density, and we are going to approximate it. And this is something which enters energy-based models, which are where Boltzmann machines are examples of. We are going to look at diffusion models, and then we are going to look at variational autoencoders. So these are methods which are widely popular, and diffusion models are some of the perhaps more popular models nowadays for generating new images. Then we are going to, we already have looked at autoregressive models. Recurrent neural network is actually our autoregressive model. And we looked at LSTMs. So this is something which we have in a way covered. But then we have the possibility to implicitly study the density. and that is given by generative adversarial networks. I see that there is a comment in the chat here. Yeah, transfer learning is actually often very much used, and I'm going to say something about how transfer learning integrates with these generative models. So as it says here, before training the data, is it better to use transfer learning or transfer learning, same as training the data? So transfer learning is often, the way you can think of transfer learning is that you have pre-trained a network on a specific task, and then you would use this pre-trained network as input to another network. So I often do that when I'm looking at quantum mechanical problems. I would then use a pre-trained network on the ground state of the system, and then I would let the system evolve over time, which means that I do what's called a physics-informed neural network, and then I solve a time-dependent equation. But that needs an input. So in a sense, that could be an example of transfer learning. There's a comment from the audience here.
Self-supervision.
Yeah.
Where you have the patients in the
yeah.
Explicitly training the network, find relationships that they know are in the data.
Yeah.
And use that as
yeah. So you, as a comment from the people in the audience here, you can actually, if you know some specific features in the data, you can pre-train on that, and because you know that that would be in the data, and if you have ways to pre-train a network before that, you will then have a pre-trained network with those specific features. And what many people often do, if you think back to what we had last week with autoencoders or principal component analysis, you could then, from the principal component analysis, you could narrow down the number of features which are relevant, and then you could train a neural network with that and have that as an easier entry point where it's easier to train a neural network. And then you would have a pre-trained network which has been trained on some selected features which you believe are the most important ones. That's how you could use the principal component analysis method which we discussed last week, or autoencoders. So it's pretty common when you look at many of these methods to actually have some kind of pre-trained input. So I do that continuously. So this is roughly the layout. We will not say anything about normalizing flow models, but we will focus on energy-based models. This is where we're going to start today. And then we are going to develop codes for that. We are going to apply this to the exciting MNIST dataset as an example. And then we will move to variational autoencoders before we switch to diffusion models. So variational autoencoders is an example of actually using Bayesian statistics again and again. And that's why we are going to say a little bit about Bayesian statistics during the lectures today. So I'm bringing back some basic elements of statistics here. So let's just do that and increase the fonts a little bit. So Bayes' theorem is something which you will see again and again. And you could now think of having two data sets. So you have two domains of events, X and Y. And each one of them are described by their own probability distribution, P of X and P of Y. Then we would often ask the question, what is the probability of X and Y? So the union of X and Y, so that's the sum. So these are axioms from statistics, which I'm just stating. And that is given by the probability of X plus Y minus the disunion of X and Y. Then we have the product rule, which is also defined as or called the joint probability. So this quantity here is then given by these expressions, where the first one here is what we call the conditional probability. So P of X given Y multiplied with the probability of Y is identical to the probability of Y given X multiplied with the probability of X. If these are independent and identically distributed events, which often is the case, then this probability Pxy, so the probability of finding X and Y, is given by the product of the two probabilities. And if they are identically distributed, P of X and P of Y are the same probability distributions. So these are just some basic statements from statistics, which we are going to need in this analysis here. Because what we are going to optimize now is a probability distribution. So we are not going to optimize a cost function like the mean squared error or the cross entropy as we have seen before, but we're actually going to find the probability which maximizes the likelihood of a specific event. That's the basic philosophy of the optimization algorithm for generative models. So the things which we have here lead also to one quantity, which is called the marginal probability. And the marginal probability is us now summing away one of the features. So if you look back, here we have a probability of X and Y. But then we want to get rid of Y. And we just want a final probability as a function of X. So that means that if these are discrete events, we would have a sum. If these are continuous variables, we would have an integral. And we would integrate away the degree of freedom represented by Y. Then we can use the product rule for probabilities, and we can actually rewrite that in terms of the probability for Y equal to this specific event, and multiply with the probability of getting X given Y. So this is us just using the product rule in the equation for the marginal probability. So when we are setting up the generative methods, what we actually want, because our probability will depend on hidden variables, we are going to integrate or sum away the hidden variables. And at the end, we just want a probability in terms of one set of variables where these x's could, for instance, be the positions of different particles, just to give you an example. And the conditional probability is another thing which we will need in the setup of the equations. So everything you will see now in the coming weeks, when we are going to derive Boltzmann machines, energy models, variational autoencoders, and diffusion models, will be based on this. Same with the GANs. So these equations are actually the important equations, which you will see us using in the final setup of a given algorithm. So these are the basic statistics ingredients which we are going to use again and again. The conditional probability is also important. So we are again using the product rule. So Bayes' theorem, even though it's, when you hear the word theorem, it's always a bit scary because you think there is some involved mathematics behind it. To derive Bayes' theorem is extremely simple. It is just based on the product rule, conditional probabilities, and the marginal probability. So Bayes' theorem is us setting together these quantities. So the conditional probability, assuming that P of Y is larger than 0, is actually given by the probability, the product rule, divided by the probability of finding Y. And this could be the marginal probability, where we simply have inserted this factor here. And then if you combine them, you can get Bayes' theorem, where you now use the conditional probability with the marginal probability and the standard product rule. And then you can rewrite this probability for X and Y in terms of Y given X times the probability of X, divided by this factor here, which becomes a normalization factor. Now, this is called, in statistics, it's called the posterior probability or the posterior distribution. So if you go into Bayesian statistics, this is now the quantity which you want to have. That means that you have a model for this probability, which is often called just the likelihood. So this is the likelihood of Y given X. And this quantity here, which you see, the P of X, is called the prior. So all these probabilities here are generated by a model. And you could now, for instance, suppose now you are looking at the number of buses which will bring you to the university. And you could now imagine that there are 6 buses which can bring you close to the university from where you live. And then you want to assign to these buses the same probability. So that could be the uniform distribution. That means that the probability, if there are 6 buses, there's a probability of 1/6, and that would define your prior here. So that means that you simply assume that this is given by a uniform distribution, which is a constant, the same probability for all these events. Then you can then give the probability here. So this x of y is now the probability of getting to the university, given that you take these and these buses. And then this will be the likelihood which you have in here. Now, this theorem is extremely simple, but you will see that we are going to reuse it again and again and again in all these models. And the interpretations are actually something which I wanted to give you through a simple example here. And this is an example which I borrowed from a textbook by Murphy. And in this case, if you now look at, this is an example of scans in mammography in order to rule out breast cancer cases. So we define the sensitivity for a positive event by the variable x. So you do a mammography scan, and the probability of a positive event is now given by this variable x. So it takes binary values, x equal to 1, representing a positive event. And you could think of a positive event as a benign tumor or not a tumor, and a negative event as having a tumor. So then we reserve y as a classification parameter for either a negative or positive breast cancer confirmation. Okay, so this is the variables which we're going to have. So positive here actually means having breast cancer. So sometimes these kind of words are a little bit inverted. And if you let y equal 1 represent the case of having breast cancer and y equals 0 as not. So what you could do now, suppose you run such a scan. So this is the probability you would have if you have cancer to get a probability from the mammography that there is a cancer case. So this means 80%. And that sounds dramatic. So 80% cases of cancer. This is actually what we are saying now is not the correct question. Because the question we are actually posing here through that probability is what is the probability of having a positive event given that you have cancer? But what we want to is actually what is the probability of getting cancer? So if you look at the various national surveys on breast cancer, the general likelihood of developing breast cancer is a very small number. So the numbers which you see here are numbers which I have made up. These are just made up numbers, okay? So they may not be true, but in general, it's a very small number. So I'm just assuming that the prior probability of in the population as a whole is very small. So y equal 1 is having breast cancer. So this is a small probability. Now, we also need to account for the fact that the test may produce a false positive result, false alarm. So we could now say that suppose this is a case where y is equal to 0, no breast cancer, but then your mammography gives a wrong interpretation or gives a wrong result. So this would be a false result, and we just give that a probability of 0.1. But now comes the question. So if you look at the reverse question, so this would be the likelihood of a positive event given that you have breast cancer. Now, the question you should pose rather is, what is the probability of getting cancer in case of a positive event? You see the wording? Because if you limit yourself to that one from the mammography, this is the output from the mammography scan, that if you have cancer, it outputs having cancer with 80%. okay? But you should turn around the question and say, what is the probability of having cancer, given that the mammography spits out a positive test? Is the distinction between the wordings okay? Too trivial? It's important because it's the way you ask the questions. Now, if I ask the questions in the second way, which I would call the correct way of asking the question, then I can use Bayes' theorem because now I have these probabilities. So if you go back to Bayes' theorem, you will see now that we could use this quantity here. We can invert y and x. So we have actually inverted y and x. So we need a model for the prior, we need a model for the likelihood. And then we can go down, if we do that, we invert y and x, and that means that I need the likelihood for x given y multiplied with this prior probability, which I put to 0.04. And then I have this normalization factor here. And if I do that, then there is a 3% chance of having breast cancer in case x is equal to 1. So this is much, much smaller than 80%. And this would be the more correct way you would ask the questions. So keep in mind that these probabilities are just numbers which I made up. They may not correspond to what you might have from a real mammography scan. Okay, so this number is a little bit more assuring. The other thing which we need now, besides Bayes' theorem and these marginal and conditional probabilities, so these are calculational ingredients which we need for generative method, is something which some of you may have met before, which is called the maximum likelihood estimation. This is essentially us looking at the different probability distributions and asking ourselves, which are the parameters which maximize the probability? So we are not interested in a probability which minimizes the probability. So minimizing the probability, we know what that should be, 0 probability. So we want to have a probability which maximizes the output or the events which we're looking after. So we don't want to have a small probability. That sounds also logical, right? So we're actually looking after a maximization problem. And what we're going to assume now in many of the calculations here is that the different stochastic events are distributed as independent and identically distributed events. So that means that we will have this situation which we have met earlier, which is called independent and identically distributed. So in statistics, maximum likelihood estimation is a method of estimating the parameters of an assumed probability distribution. So we are going to train this probability distribution with the data which we have. And we want to maximize this probability. And the parameters which we're going to train are often parameters of some kind of neural network or some complicated network. And in practice, we are going to maximize the logarithm of the probability distribution because that's easier to maximize than a product of probabilities. So I'm coming back to what this means for us. So the aims here, before we switch to the whiteboard, is as follows. So we are going to look at the following methods. We are going to look at energy-based model, where we start with the Boltzmann machines, which is a familiar starting point for many of us. And then we are going to move to variational autoencoders. We are going to look at diffusion models, which follow immediately from variational autoencoders. And then we will look at generative adversarial networks. So these are 4 extremely popular methods in the field of deep learning nowadays. And if we get time at the end of the semesters, we will say something about transformers, reinforcement learning, if we get time for that. Any questions so far? So I hope the statistics review is okay. These are some basic elements which some of you have encountered in, let's say, one of the first courses in statistics. The marginal probability, the conditional one, and the product rule. These are quantities which we will be using again and again in the analysis which comes. So I would also like to say something about energy models, because the way you are going to meet them now is that we start with the Boltzmann distribution. And the Boltzmann distribution takes the energy as an argument of a system, of a physical system. So this is something which has been developed for statistical physics, but you don't need to have a model for the energy. So what people have done, and if you go into Foster's textbook, you will find the modeling of this probability distribution, where this energy is replaced by a convolution neural network or a recurrent neural network. And these methods have been demonstrated to be extremely powerful in fitting data and making efficient probability distributions. Any questions so far? So because now I'm going to, after this long introductory session, I'm going to switch over to the whiteboard for the rest of the lecture today. And we need to go through some of these small technicalities, which we are going to elaborate more on next week, when we are going to develop codes, etc., for Boltzmann machines, and then later for the different methods like variational autoencoders. And finally, we will also look at, after variational autoencoders, we are going to look at the diffusion models, which can be seen as a kind of extension of autoencoders. Okay, so let me switch to the whiteboard. I think everybody should be able to see the whiteboard now. So what we are going to assume, as I said in the lectures here, in the slides, is that we have what are called identical and distributed and independent variables, IID. So that means independent. This is an assumption we are going to make about the data set. Independent and identically distributed. That means that there is the same identically distributed. We met that already in the previous weeks when we discussed the PCA and its connection with autoencoders. We are going to assume that there is a domain of events. And I'm just going to call this X, upper letter X, uppercase X. And this contains a lot of different types of events, up to some X minus 1. So these are stochastic variables, all of them. So just keep that in mind. These are stochastic variables. So we are going to define a probability distribution, which is now given by the product of all the different probabilities for the different specific events. So that means that the total probability distribution now, X, for these domain of events, is now going to depend on a set of parameters, theta. So these are parameters. And we want to optimize these parameters. We don't know them in the beginning. And we are simply going to assume that this is given by the product of the different probabilities up to n minus 1 here. And these are the probabilities which follow this domain of events. And we have an X of I, and each of them depends on these parameters. This is the assumption we are making now, based on having independent and identically distributed. So this P underscore uppercase letter X, this is the probability of a given event. And the total probability is just a product of these. Like you would set up a product of Gaussians for multivariable cases, where you could have, let's say, 2 variables, which are then given by the product of 2 Gaussians. That's just a typical example. So what the optimization problem which we are looking after is, and this is the maximum likelihood estimation. So that is given by an optimal parameter, theta, which is given by argmax for the variables theta, which we have. This could be the network parameters. So your function could be a neural network, which you want to optimize. And if you have thousands or hundreds of thousands or millions of these, you would then optimize with respect to all these parameters.
So what we are going to do now is simply to optimize this quantity here. So that means that we need a gradient. And since we have a product, it's much easier to take the log of the probability than to take the derivative of the log than to take the derivative of a product. So typically you transform this problem into the optimization of the log of that problem. And you can do a minimization, but then you take minus log. If you do an maximization, you would then typically have plus log of a function. Now, the maximization follows obviously from the fact that we don't want to have a minimal probability, which we know is a number void of interest, it's 0. So we want to maximize the probability. So in general, what we end up with is that the optimization problem is then given by argmax of theta, and then we take log of this function, p of x, which means that the product turns into a sum. Or we can set up theta as a minimization problem, and then we will simply minimize with respect to theta as argument, minus log of p of x given by these parameters theta. So that's the kind of overarching input which we are going to look at now. Now comes a problem. How do we define this probability? How do we make up a model for this kind of probability? And I'm going to show you now the type of function which we are going to deal with. So the first encounter for such a probability distribution is the Boltzmann distribution. And many of you may have met that. So our first encounter and these are very powerful methods for fitting a probability distribution. That is the Boltzmann distribution. This follows from statistical physics and thermodynamics, but we are going to be much more flexible than that. And this function which we are going to fit could actually be a neural network, or it could be a convolution neural network. But we are going to look at the Boltzmann distribution as our first encounter. And that leads to this class of models, which we are going to call in a generic way as energy models. So this is our first encounter of generative models. And as I said, they have gotten a revival because you have much flexibility in choosing the function you want to optimize. But if you now look at the Boltzmann distribution itself, this is in physics given by a probability where you have E of I. This is the probability of being in a state with energy I, EI, with a temperature beta. This is the inverse temperature. So this is you read this as a probability of being in a state I, which has energy E of I at a given temperature. This is the way you read the Boltzmann distribution. So this is the energy, and this is why these are called energy-based models, simply through the name of the basic Boltzmann distribution. This quantity here is normally called the inverse temperature. And it's given by 1 divided by Boltzmann's constant times the actual temperature which you have. So these probabilities change with temperature. So if you have a very low temperature, it's very unlikely that you will access other possible states. You will mainly be in the lowest lying state, that the states normally called the fundamental state or the ground state. But then if you heat up the system, then the probability of jumping into other states becomes more likely. But if you have a very low temperature, as you can see from the distribution here, this is given by this function here, minus beta times E of I. And then there is a famous function here, which depends only on beta. And that's called the partition function or the normalization function. So this is a normalization constant. And let me just set it up. So for those of you who have taken a course in statistical physics, this is called the partition function because it looks at all the ways you can partition the system in terms of specific energies which you can access. So this is now given by the partition function. And this ZOB, this is the nasty part. And you will see that after the break, this is where all our problems are going to be buried. So COB is given by a sum over all these energies which the system can access. And this is in principle an infinite amount of energies. So the calculation of this normalization constant is something you want to avoid. This is, you could say that all the physics for the Boltzmann distribution is buried in that function. And you can use, so statistical mechanics is an extremely elegant theory. You can derive all of the thermodynamical relations, the so-called Maxwell equations used in thermodynamics from this quantity. And this quantity is simply you listing up all the microstates which the system can access. Unfortunately, the number of microstates is infinite. So the calculation of that animal there is actually the one which is going to be our main problem. And you will see that after the break. So we are going to replace this quantity here, this E of I, with either a neural network, a convolutional neural network, or some simple functions defined by the parameters of a neural network. And that means that beta is not going to be a parameter for us, but the parameter which we will have, and you will see that after the break, is actually the parameter theta of the model. So when we are going back to the optimization problem itself, we are going to have to calculate a gradient of this quantity here, which now will have the normalization factor in the denominator. You also see the benefits of having a log of a probability, because you will have a log of this quantity here. So that means that the exponential of a log simplifies. But then you will have this quantity, which we need to evaluate the derivative of. And that's where the problem is. And the different methods you will encounter, like variational autoencoders, Boltzmann machines, diffusion models, etc., they deal with different ways of handling the derivative of that function, which is unknown. So keep also in mind that the function you're going to produce will be a multidimensional function. That means to sample from this function E can be extremely difficult. So we need to have efficient sampling algorithms for setting up, even if you have an analytical expression. So if I were to be able to calculate this partition function, and this is, for instance, a 1,000-dimensional function, every time I call it, I would have to do an infinity of floating point operations just to get out a probability. So sampling from the probability, even if you have a nice, beautiful analytical expression, can be as difficult as obtaining it almost. So there are many small bottlenecks, which we will discuss in more detail in the coming lectures. But now you guys deserve a break. So let's do that. And now I have to find my drawings here. Here we are. So you should all be able to see this one again. So let's take now a more in-depth look at what is Boltzmann machine and what it means mathematically, that what we have to do here. So a typical example of this function E, which you will encounter. So let's just set that up before we proceed to the calculational ingredients which we have to deal with. So a typical function for this E could be something like this. And this was one of the traditional or first type of Boltzmann machines which was introduced. This is something which we would replace now with E of X, and I'm going to put this X now can be a vector, it can be a scalar. I'm just going to leave it like this. And then there's a parameter which represents the hidden layers. And then we have a parameter theta here. And the one type of model for this has been to define these X of I's, which we're going to set up the inequation in terms of a binary model. So it could take values 0 and 1. And the H of I's could also take binary values, 0 and 1. It doesn't need to be 0 and 1. It could be -1, +1, etc., as long as a binary case. So this is normally called a binary Boltzmann machine. Now, this function E, which we have defined here, which enters this exponential, in its simplest form, is given by something like this. So we would have an I equal 1 up to M, and M is normally called the visible layer, and we would have our variable X of I multiplied with a bias, if we now borrow from the language from neural networks. So this is something which we can rephrase as a neural network. So we have a J, and then we have an N here, which we call the hidden layer. So there is a new parameter, a new bias, multiplied with this value H of J, and X and H can only take binary values. Plus, and then we have some coupling. And that means that we are going to have a weight matrix, which kicks in here. And this sums over M and N. So we would have an X of I, and we have a weight parameter, Wij, multiplied with H of J. So this is now something we would call the energy model. Now we can translate this into something which looks like a shallow neural network. And the way you can portray that one, if we now just put on some namings of the constants, so this would be weights to be trained. And this B and A, these are the so-called biases. That means that this theta is a collective container for A, where A now is a vector which contains all the A's, the B's, which is a vector, and a matrix W. That means that you can now set up something which looks like a neural network, and then do the training of these parameters by optimizing, let's say, the probability distribution. So a typical model then could be you setting up a set of hidden nodes, and then we have an H1, H2, and this goes all the way up to H of N. Then we have some input layer. This is normally called the visible or input layer. And this is called the hidden layer. And then we can have contacts between these different nodes. So we can treat these as nodes as before. So this will be up to an X of M. And there is no connection in the layer. You could actually do that. So the original Boltzmann machines had connections between the X's and the H's. This turned out to be very difficult to train. You can also stack these layers. You can have more hidden layers. And this is normally called a deep Boltzmann machine. What you're going to see here is a shallow machine, which is normally called a restricted Boltzmann machine. And this is the one we are going to look at because it's pretty easy to set up the probabilities which we have to code if you use that as a model. So that means that we would have connections between all these guys here. So this would connect with that one and all the other ones. And the same with the X1 connects with all the other ones, X2, etc., etc. Now, you see now immediately that this is something which we can modify, this function E. We could now, instead of having this shallow model, we could replace that with a convolutional neural network, as an example. But the probability function which we need to train would still be something which looks like this. But now we have to change some of our notations a little bit. because we have introduced these hidden layers. So the total function E depends on X and H. That means that there is a probability distribution, P of X, of H, of theta, which is given by, let's say, this E to the minus E of X, of H, of theta, divided by this partition function, Z of theta. So instead of having Z of beta, which was the inverse temperature, we are now having a partition function which is defined in terms of the parameters we want to optimize. So that means that our C of theta, this is a constant. Just keep that in mind. It depends only on the parameters theta. So this has a sum over all the x's which you can have. So if you have m x's, you see now that if you have m x's, you have in total 2m configurations. 2m ways, because this is a binary system. So the way you can distribute these x's with zeros and ones, or minus ones and plus ones, is given by 2 to the power of n. And this one has obviously 2 to the n ways we can distribute them. So here, this x here sums over all these possible configurations here. And it sums over all the possible configurations of H. So I just write this in a more generic and compact way. And in this case, I would now have e to the minus e of x of H as a function of theta. So this is now my normalization constant. And you see that if you have a simple case, if you now have, let's say, 2 hidden nodes and 2 visible nodes, if you say now that m is equal to 2, that means that the x's can take the following values. So you can have 0, 0, you can have 0, 1, and you can have 1, 0, and you can have 1, 1. So that means that the total number of configurations, total configs, is then 2 to the power of m, which in this case is equal to 4. So if we then look at n equal to 2, that means that our h's can take exactly the same value, 0, 0, 0, 1, 1, 0, and 1, 1. So that means again that we have the total hidden configurations is 2 to the power of n, which in this case is also 4. So that means that when I am looking at this energy or this function, this explicit value, given this choice, which I have here, this specific choice, then I need to have a sum here which goes over the 4 ways I can distribute the x's and the 4 ways I can distribute the h's. Now, this is normally what we would call a baby case, because often if this is an image you want to train on, this image can have something like, let's say, 20 times 20 pixels, which means that you would have 400 visible nodes. And that means 2 to the power of 400, which becomes pretty large. So you see quickly that the calculation of this quantity here is something which quickly, very quickly blows up. So the handling of that one is one of the delicate topics which we have to deal with. The other thing you should keep in mind is that at the end, I don't want to have a function which depends on x and h, but I would like to have only a function which depends on x, because I couldn't care less about the hidden nodes. The hidden nodes function as a way to introduce non-linearities, which we can train and hopefully get a better fit, like you did with neural networks. But at the end, I want to integrate or sum away the hidden layers, because what matters for me are the visible nodes. And you could think of these x's as the positions of a given set of electrons. So if you have 10 electrons in 3 dimensions, you would need 30 input nodes. one node for every dimensionality and for every electron. And that means that this is the quantity I want to give you if I want to find a probability distribution for how 10 electrons live in 3 dimensions. Then I would like to train such a probability distribution. And in that case, I'm not interested in the hidden layers because that is something you can think of as an additional parameters in the optimization part, which may bring in some wanted nonlinearities. So the other thing which we want then is this marginal probability. So which I'm going to repeat now. So the marginal probability which we are interested in is going to be P of X as a function of theta, which means now that I have to perform a sum over H. So I'm leaving it unspecified. So H would in general be a vector. So I'm just summing over all the possible configurations. And then I have e to the minus beta. No, not beta. I don't have that one here anymore. I don't have x of h of theta divided by z of theta. So z of theta is a constant. Just keep that in mind. And it depends on the parameters which we are going to optimize. So this is the quantity which at the end I want to obtain, because that's the one which is going to tell me where these different particles are. Or if I want to draw images of horses, these x's are going to represent the pixels, which then contain important information about the features which allow you to distinguish between a horse and a cat. Okay? So what I'm going to do now is simply to stay with this P of X, and we're going to look at the optimization part, because that's where we will see the clear bottlenecks in the equations and why we need Monte Carlo sampling and Markov chain Monte Carlo sampling. So the optimization part is the crucial part. So this probability is P of X of theta is a quantity which is larger or equal than 0. We are going to assume that it can be normalized. So it means also that it should be less than a infinity. What we need now in the optimization is to find theta here, and this is going to be arg max or arg min of theta of log of the probability of P of X of theta. So now keep in mind that this P of X is already the quantity which we call the marginal probability. In practice, this means for us that we need to take the gradient. So this means that we need a gradient with respect to theta, and we are going to drive that to 0. So we have the gradient of log of P of X theta, and we want that one to be 0. So what I'm simply going to set up now is the type of equations which we are going to get. And I'm going to make a small simplification here so I don't carry all these expressions with me. So I'm simply going to say that this quantity which you see here is now a quantity which I call f of x as a function of theta. Okay. And let me quickly remind you of my probability, because my probability, when I take the log of P of x of theta, that is going to be given by all the xi's, the individual ones defined in the domain of P of x of I of theta. So previously I had an x here, but I'm going to skip that just for notational economy. Is that okay? And D is the domain of possible stochastic events. So if I now take the log of that one, that clearly means that log of the P of x of theta is simply going to be given by a sum over x of I. And for notational economy, I'm also going to skip element in the domain. So now it's by implicitly assumed that x of I is an element of that specific domain of stochastic variables. And this means that I have log of P of xi of theta. And when you now look at the derivatives, this is now where we have to start looking at things. So this quantity here is nothing but x of I. And then I have log of this function, which I defined as f of xi of theta. Okay. And then I have my denominator, which is minus. And then I have a minus log of z of theta. So I'm just going back to the equations here. And what I've done now is simply to replace this whole exponential in terms of this function f. And that's why when I take the log here, I have plus here and have minus for the denominator. Okay? Everything okay? So now I take the derivatives. And if I take the derivative, I have to be, in particular, I have to be careful. So when I take the derivatives, what I need to look at now is the gradient of, in particular, of this quantity here, which is the one which is going to be problematic. Now, the previous one, the log of this function, is a little bit easier to calculate, although this guy here is a multi-dimensional function. And it can be time-consuming to actually extract variables or expression from that. But this is something which we have a model for as a function of theta. Okay? So the difficult part is actually going to be this term here, because if you look back, this is a function which in principle implies sums over infinitely many configurations. Even if I have a small number like 100 here, I will have 2 to the power of 100 possible ways of arranging the x's. And similarly, if I have an equal amount of hidden nodes, I will have a similar amount of configurations. So that means that these sums here are ugly beasts to evaluate. So let's now look at the calculation of the quantity here, which is the one which is going to be problematic. And essentially all these methods, when you look at diffusion methods, when you look at the variational autoencoders, it's going to deal with variations of how we calculate this expression. So if you get this overarching message about the log C of theta, then you have the essential problems in all generative models. So let's now look at the explicit evaluation of this term. So if I look more closely at it, this is something which I can write out as a derivative of theta. For those of you who have taken a course in statistical physics, you know that the log of the partition function defines Helmholtz free energy. Helmholtz free energy is the difference between the expectation value of the energy minus temperatures times entropy. And it's given in terms of log C times minus temperature. So this quantity which you see here, before we take the derivative, in statistical mechanics is one of these fundamental quantities which we deal with. Now, the derivative is pretty straightforward to evaluate, but you will see now that this is something which we will need to rewrite, because this is going to be given by theta, and I'm solving over all the xi's, and I have this function, x of I have integrated or summed away the hidden nodes, divided by z of theta, okay? Obviously, I can rewrite this one as a sum over x of I, of f of x of I, it's a function of theta, divided by z of theta. And now comes a neat trick, which you can often use when you have ratios like this one, where you have a function in the denominator, which is the same as the derivative. It's actually the function is the one which gives you the derivative in the numerator. You can now, by a small trick, we can now rewrite f of x of y of theta. And these f functions are often given by exponentials, but there is nothing which hinders us in writing it out like this, of f of x of y of theta. If I do that, then I can rewrite this function which I put up, this d theta, the gradient divided by c theta. That. I can rewrite this one now as a sum over the xi's, and then I have the gradient, and then I have my exponential, and then I have my log of f of xi theta divided by z of theta. And if I now rewrite that one, if I take the gradient of that, I'm going to have a sum over xi, and then I'm going to get the exponential. So this is us just using the expressions for the derivatives. So we'll have an f of x of I of theta. And this is multiplied with the derivative of log of f of x of I of theta divided by z of theta. Okay? These are just simple manipulations which I'm putting in here. Now, if I now look a little bit closer at this expression, if we take this one, we know that this is nothing but the f of x itself, this quantity here, right? So it means that if I now put it back in here, then this equation is nothing but f of x of I of theta. Now comes a very nice thing, because my p of x of I of theta is actually equal to f of xi divided by this constant, c of theta. So keep in mind that c is a constant. So what I can do now is to rewrite this function which you have here, divided by this one as my probability times this quantity here. And that looks like a standard expectation value. And this is the way we end up evaluating that quantity. So we end up with something which looks like x of I over the domain of all possible events which we have of p of x of I given theta multiplied with d of log, and then I have f of x of I of theta. So that's my expectation value. And this is something we would write out as an expectation value. It's actually a sample expectation value, unless we can do all the possible stochastic events. So this is the expectation value of log of f of x of I of theta. So that means that my gradient, the quantity I need to optimize, the optimization part. So the optimization part is now given by the following expressions. So I have my d theta of my probability p, which I want to drive to 0, which is simply given by the following expressions. So I'm going to have a d theta of log of f of x of theta minus the expectation value of d theta log of f of x of I theta. So that is my quantity I need to evaluate. Now the bottleneck is actually in the calculation of the second term. The first term is often called the positive phase. The last term is called the negative one due to the negative sign. Now, the way you would evaluate this one, although even the first term can be tricky because f is a multidimensional function, but the second term is something which we need to evaluate with Monte Carlo sampling. And that is where Metropolis or Gibbs sampling or Langevin sampling or other methods come to our rescue. So let's set that up. So the term which is going to cause problems for us is this one. And you will see this one written in different disguises later. But what we are going to do now is to evaluate this term with Monte Carlo sampling. And the way we would typically do that is as follows. X of I of theta. This is approximated with 1 over m, where m is the number of Monte Carlo samples. And the sum over I equal 1 up to m. And then I have my derivative of log of f of x of I of theta. So what we definitely need, we need to have a model for f. This defines a specific model which we deal with. So this could be, as it's written in Foster's book, an example where you use a convolution neural network. It could be a neural network, a recurrent one, or it could be a simple Boltzmann machine, which we will discuss in detail next week. Because then I wanted to step you through all the basic ingredients which you need in order to set up your own program for a Boltzmann machine. So the mathematics which we often end up with or are stuck with is actually this one. And this is solved with Monte Carlo sampling, or normally what is called Markov chain Monte Carlo samplings. Often this is just called MC squared. Monte Carlo, MC Monte Carlo Markov chain. And the key ways, the key ingredients which you need in here is obviously a Markov chain. So we're going just to remind you quickly about the theory of Markov chains. So just as a quick reminder, then we will need the way to sample, and the sampling rules which are often used here are not the Metropolis sampling, but Metropolis is one of them. So Metropolis Hastings. And Metropolis Hastings involves ratios between probabilities, and it's often more time consuming to use in this type of calculations. Because now you're going to calculate this one. If you have theta being the parameters of a neural network, this can be millions of parameters. And you're going to optimize that function for millions of parameters, and that will be extremely time consuming when you do the Markov chain sampling. That means that you want to have quick ways to sample and accept a new suggested move in the Markov chain. So the Markov chain is actually you proposing new random states and then having a rule by which you accept this new suggestion or reject it. So Metropolis is one of the algorithms which you have heard of. Then there is another famous physicist, which is called Gibbs. So you will encounter many of these famous physicists in these ways of doing the sampling. So Gibbs sampling is one of the recipes we will discuss in more detail next week, which is the one which is used. Then when we come to diffusion models, there is another very popular way, which is called Langevin sampling. So these are different ways of doing this. And you will notice that as soon as you cook up an efficient way to perform this calculation with generative methods, this is a situation, if you cook that up, you will get many new friends, as I've said. And these are friends which will cite you. Because the way you calculate these expectation values, so as I said, the bottleneck is you having to evaluate this expectation value here. And you want that to be fast and obviously reliable. So one thing we need to remind ourselves a little bit is about Markov chains. So I hope it's okay if I just give a quick reminder of the mathematics of Markov chains. Is that okay? Just to give you a very short reminder. So if we now look at Markov chains, this has always been one of my favorite topics. You can derive from a Markov chain the diffusion equation, which is a fantastic thing. So it means that an important physical process like diffusion is intimately linked with Markov chains. So what I'm going to define now is a probability. So my P of X of I of a given theta is something which I now will replace with a P of I. So I is a state the system can be in. It could be a position, or it could just be a specific energy state it could reach, or any other state. And this, instead of theta, I'm going to have time. So you can now think of some kind of time, either real or artificial time, where you now define a probability distribution. So since this is a probability distribution, it means that if I sum over all the events in a specific domain of P of I at a given time t, this sums to 1. So that's my standard requirement for a probability. Then I'm going to define the probability for making a transition. And I'm going to label this one as a Wij. And the way we can read this is, I'm going to put an arrow here, is you making a transition from a state J to a state I. Okay? So I'm going to use that notation because that is something which becomes a little bit more intuitive. But we assume that such an object exists. This is going to be defined as a stochastic matrix. So if I sum over all the columns of this matrix, this sums to 1. So we assume that this is a stochastic matrix. Which means that the largest eigenvalue, so if we now order the eigenvalues so that we have a lambda 0, the absolute value larger than lambda 1, etc. And if this matrix has dimension m times m, there is a final eigenvalue n minus 1. And this lambda 0 is equal to 1. That's the largest eigenvalue. So a stochastic matrix has columns or rows which sum to 1. They are normalized. And it has as the largest eigenvalue 1. Now, what I'm going to assume now, and this is the basics for a Markov chain, is that if I now make a new time step, t plus 1, this is given in terms of all the states which I had previously and the transitions which I can make. So if you go back to the definition which I put up, this is just a matrix times a vector, which we can write in a more compact way. So Pj of t. So instead of looking at the different i's, you can think of this as a vector. So if you have a vector p here of t plus 1, we can write this in a more compact way. This has a w times a p of t. And we've made the assumption that this transition probability is time independent. We can make it time dependent, but that complicates life a little bit. But what happens is that this equation which you see, the one in the middle, is the definition of a Markov chain, where your next step is independent of all the steps which came previously. So it depends only on the step before. So this is where you are, the probability. You could just think of you having at the initial time t equals 0, a cup of coffee, and you put a drop of milk into it, or some milk, and that is distributed as a spike around where the milk drop comes in. And then after some time, these milk molecules diffuse in the cup of coffee, and you reach some kind of equilibrium where you get a milky-like cup of coffee. And that would be the equilibrium situation. And when equilibrium has reached, or you have reached the most likely state, then P of t plus 1 becomes equal to P of t, and you would just write that as P. So this is the most stationary state, or equilibrium state. So I am, I'm not going through every derivation here. I'm just stating some of the basic properties. Now, one thing you could do now, if you now look at these equations, if you look at this equation here and you take away time, this looks like an eigenvalue problem because you have a vector here. There's no time dependence anymore because we assume that. There is no time dependence here. So it's a vector equal to a matrix times a vector. And that means that the eigenvalue is equal to 1 here. So this looks like a standard eigenvalue problem with eigenvalue equal to 1. Now, what happens is that when equilibrium has been reached, is that the most likely state, or the stationary state, or the equilibrium state, as it is called, is the state which has the largest eigenvalue here. And you will see that when you model, you can set up a simple matrix, W. Suppose you do a 4x4 matrix, which is a stochastic matrix, and you act on that on an initial state, you will see that when this evolves as a function of time, it will reach one state which doesn't change anymore. So you can risk of getting into cyclic states in a Markov chain. So there are ways to prevent that. And one of the requirements you put in the equation is something which is called detail balance, which I'm going to state quickly now. You can make some further analysis of this problem here. If you now think of the eigenvalues of W and eigenvectors, so assume that you can diagonalize this V of I, and it has an eigenvalue, lambda of I, of V of I. So what we could do then is simply to expand P of t equals 0 in terms of this basis. So P is now a vector, and we could expand that in terms of, it could be one of these components. So it could be a P of I here, which we then expand in terms of the components of alpha I, now alpha j times V of j. And this alpha j here is actually equal to the overlap between P of I at t equals 0 with V of j. So we have a complete basis, and we can expand a function in that complete basis. So if I now go back to the notation which I had, I'm going to skip these i's, and I look at the action of W on P of I at t equals 0, and later I will skip these subscripts. This is nothing but j of alpha j on V of V of j. And this is the same as a sum over j, alpha j's, lambda j's of V of j. Now, I can repeat this many, many times. So if I do that t times, and I assume that there is a time step of 1. So if I now look at my P of I of t plus 1, this is simply going to be given by W acting on P of I at time t equal to 0. So I can put t equal to 0, so to the first time step. And now I can repeat this many time steps. So if I do this, if we do this, tau steps, what happens then is that I have my P of I of tau is given by W acting tau times on P of I at t equal to 0. So I have a time tau, which is all the number of steps I've made. And if I now look at the equations which I put in, this is going to be the same as this linear expansion of the alpha j's. And I'm going to have lambda j to the power of tau and multiplied with V of j. Now, if I also know that the largest eigenvalue is the one which is called lambda 0, I can rewrite this as an alpha 0 of V0 times lambda 0 to the power of tau. this is equal, the largest eigenvalue is equal to 1. And then I have all the other ones which are small, j different from 0. And then I have my alpha j, lambda j of tau of v of j. Now, depending on how large the second eigenvalue is, if you now let tau go to infinity, this is going to be, the second term is going to be a series which will roughly disappear when tau becomes larger and larger. And the only term which survives then is in the limit lim of tau goes to infinity of this p of e of tau. This actually goes over to p of I, the probability, which becomes time independent, and this is equal to alpha 0 times v0. So it's one component which survives. And you will see that if you set up a stochastic matrix and act on a random initial value, you can just set up a 4x4 matrix with the only requirement that the columns sum to 1. You can set that up by hand if you want to. You can diagonalize it and you will see that the eigenvalue, the largest one, is 1. And then you multiply it with a random vector, which is normalized to 1. And then you repeat many, many times, and then you will see that there is only one vector which survives. And that will be the same as the largest eigenvalue of that matrix, if you can diagonalize it. So a Markov chain is a chain which reaches the most likely state after a given number of iterations. So on the way to achieve this kind of equilibrium situation, which is fundamental when we are going to calculate expectation values, we need then a sampling rule, because we are going to suggest moves. And every time we suggest a move, we have to have a rule which tells us, do I accept it or do I reject it? And this is what we will bring up next week. We are going to set up Gibbs sampling. We are going to set up Metropolis sampling. We will wait with Langevin sampling till we come to diffusion models. And when we have that, we are going to dive into the setup of a Boltzmann machine, a simple restricted Boltzmann machine with a simple binary energy function. And then we will show how we can actually encode that and fit the famous MNIST data. So you're going to be so fed up with the MNIST data that just naming it or hearing it is going to make you guys leave the room. Because I'm going to use that as an example throughout the semester for all the methods which we developed. So next week, we are going to look at these different types of samplings. And then we are going to dive into the setup of a plain Boltzmann machine. And when we've gone through that, we begin with variational autoencoders. So before the Easter break, we will have started to scratch the surface of variational autoencoders. And after that, we are going to use the rest of the semester on GANs, variational autoencoders, and diffusion models. And that will be essentially the main topics we cover. And if we get time, we will say something about transfer methods and reinforcement learning, if we get time. Okay, I'm going to stop here for today. So just stay tuned, and next week we're going to see how we can set up all the machinery for a Boltzmann machine.